Welcome back to SC0X. We're in week 4. We're going to talk about algorithms and approximations in this lecture, kind of wrap up our whole deterministic optimization segment of the course. So we're going to start off with algorithms, and algorithms are simply step-by-step instructions meant to achieve a goal. Now there's some formal definitions, and we'll go over that in the lecture, but you can almost think of it as a recipe. Again, step-by-step instructions. So I'm going to show examples of this using networks, because networks are so common in supply chain and in transportation. It's a good chance to show some specific algorithms used in network design. And I'll talk about 3: shortest path, traveling salesman, and vehicle routing. Now we talked about some of these really briefly in a previous lecture, and I showed how to solve them using linear programming, but I'm going to show you how algorithms can be used to do that as well. So the shortest path problem, we're going to go and talk about an algorithm called Dijkstra's algorithm. It's a very famous algorithm, and essentially what we're doing with shortest path problem, we're trying to figure the shortest path, say from this node to this node through a network, and we're going to step-by-step go through it using something called a label setting or label correcting algorithm. And so I'll show how this is done, and I'll show how it compares to doing it with a linear program. Then we'll move into the traveling salesman problem. Again, that definition is I'm going to start at any node, and I want to visit each other node once and only once, and then return back to my origin. So that's the traveling salesman problem. And we actually did some heuristics for this. We did what's known as the nearest neighbor heuristic, where I start and I go to the closest one each time. But we're going to also talk about a different type of heuristic called the 2-opt. So the nearest neighbor is what's known as a construction heuristic. It builds the tour. The 2-opt is a little bit different. So it goes through and it looks and says, well, there's 2 arcs that I can switch out. And this essentially makes sense if I have something, let's say, that goes like this, where I have a tour that crosses. And then we look and say, well, should I cross those out? Should I swap those out? And so that's known as an improvement algorithm. And so we'll go over that as well. And I'll finish up with vehicle routing. Vehicle routing is essentially like the traveling salesman problem, except I have a depot and I have multiple vehicles. So I want to figure out which customer locations to cluster together and then how to route them as well. So I might here cluster those. I might do this in a tour. So you can see it's a bunch of little traveling salesman problems. And so that's called the vehicle routing problem. We'll do 2 heuristics there. One is called the sweep, which is just like a clock. I start at some point and I start going in a clockwise or counterclockwise direction, and I keep clustering the different locations together till I hit capacity. And we'll go over that in a second. And then we'll also go into the savings algorithm. And so the savings algorithm, or the Clark-Wright algorithm, is a little more complicated, a little better, and it's widely used in practice. So we'll go through different algorithms within 3 different network problems. Then we'll turn to approximations. Why do we do approximations? Well, sometimes you don't have sufficient data, or the problem's so complex you really can't analyze it completely, so it's very helpful to be able to approximate an answer. It's also, I think, a really good practice when you start in a project, before you dive into the heavy-duty data collection and the analysis, to step back and make an approximation of what you think the answer is going to be. This goes by many different names. It's sometimes called a ballpark estimate, which is very much an American term because it means it's in the ballpark for baseball. Sometimes you hear it as SWAG, a scientific wild-ass guess. A back-of-the-envelope analysis, which a lot of the students here don't know what an envelope is because you only use email. But still, you do anything on the back of an envelope, back of a napkin. Fermi estimation, because Fermi was famous for doing these kind of calculations. And order of magnitude analysis. They're all saying the same thing. How can I make an approximation, an estimation, with as little information as possible? Widely used in science, but also widely used in business. A lot of consultancies will look for you if you can do this kind of quick estimation, because it shows that you have an agile mind. So we'll spend some time on that, and we'll go specifically into some approximations that are very useful for networks. So we'll talk about one for traveling salesmen. So for example, if these are all the locations I have to visit, I can do a really good approximation here by looking at what the area is and looking at what the number of the customer locations are. And I can find that the traveling salesman distance is very close and is proportional to the square root of n times a. And we'll show how we came up with that, but this is a very, very powerful approximation where I can make quick estimates on something with very little information. I'll also look down here, one for the vehicle routing problem, and we'll look at the big thing here is the number of tours that you're going to use, and we'll find that we can actually find that out by making an approximation of what's known as the line haul distance, which is that distance from the depot to the centroid or center of area of each of these clusters. So you can see the tours as consisting of actually a line haul move and then a traveling salesman tour around and then a line haul back. So we can find that that line haul distance can be best approximated by this factor k, which we'll talk about in the lecture, and then the straight line distance. So as the crow flies. We know in real life on networks, you never have that great distance. You actually always have a circuity factor. So we'll talk about how you get that circuity factor and how you can make better estimates. Because if I know that line haul distance, I can then determine the number of tours that I have. And we'll go over this in much more detail, but we'll use this approximation approach. I'll show you how to set bounds and things like that, but then we'll apply it specifically to these two problems. All right, so that's what we're going to cover in this lecture. Please watch the videos, do the quick questions, the practice problems, have fun.